Good evening, everyone. Welcome to the tail end of today's proceedings. I hope you are feeling suitably drowsy. I took a necessary injection of caffeine before I arrived, so good to go. I was very far thinking about this. So, my name is Abid Mujtaba. I work at Bloomberg. The gray jacket should show you. What I really want is for all of these people who've been working on image recognition to do like a snapshot of the conference and tell me what the propensity is for wearing gray / black / dark colors here in attendance, like 80%. You look around, there's a few reds and there's black. Makes sense. Okay. So I am a trainer at Bloomberg, which means I get to induct new hires, financial software engineers at Bloomberg. This talk came out, as most good talks do, from a discussion I was having with my trainees. And we were discussing memoization using decorators, and I realized I didn't actually know what was going on. And then when I sort of went in there, the talk will tell you what I discovered. So there's a lot of enthusiasm here in the presenters. It's my first time. And I thought maybe I should incorporate some zany activity. So for this talk, you can think of this as a detective mystery / with Pride and Prejudice, but without any zombies. Zombies have nothing to do in Austen's world. It's a crime against humanity. Okay, so we are going to talk about, since we're going to talk about recursion, Fibonacci, you can't get away from it. This is the mathematical description. This is a very naive implementation of it, right? So this completely matches what the description says, but from a computational standpoint, it is extremely inefficient. How inefficient is it? On this very nice laptop that my work provides for me, if I try to calculate Fibonacci for 50, my computer locks down for 3 minutes. That's pretty bad. The solution to that is, let's find out why it's taking so long. So here's the same code, but I've added, don't do this, but I've added some print function, the global variable to keep count, and it prints this very nice graph. As you go down, that's the order in which the call is being made. So when I try to calculate Fibonacci of 5, it will need 4 and 3. And look at all the repetition. 0 is calculated thrice, 1 is calculated 4 times. So we are wasting a lot of cycles doing something that we've already done, blah, blah, blah. That's why we would need recursion. How bad is it? Simple. I just did this by hand. The number of calls as n increases is obviously 1 for the first call, and then the number of calls for the recursive entries. And you can prove that this actually is equal to twice the Fibonacci number. So it grows exponentially. That's why it's so bad. In fact, the minimum number of calls you should have to make is just this. You should only need to calculate for each entry exactly once, and that's what memoization does. So you go from exponential time to linear time, which is fancy. So memoization. Memoization is the idea that you cache a result. You only calculate it once. You cache it, and the next time you need it, you just pull it out of the cache. That's what it is. So this is a very standard implementation of memoization in Python using a decorator. Decorators make this fantastic because they are reusable. They're a perfect example. In fact, that's where this came from. I was teaching decorators to my trainees, and memoization was a very good way of saying, oh, this is what a decorator is, and this is why it's so, brilliant. So you have a cache, which is just a dictionary. It's in the outer function, so it's going to get closed over. Here you have your inner function. If the number is in the cache, return the cache version. Otherwise, calculate the actual value, store it in the cache, return that, and that's it. And I've used a number instead of args to make it simple. So I take the same function definition and I just slap the decorator on top of it, right? And the idea is it should just go to the cache. So here I've just sprinkled in a few print statements to show you what's going on. The logic hasn't changed. And now when I try to calculate the Fibonacci of 5, it recursively wants to calculate the Fibonacci of 4, 3, 2, 1, 0. And the next time here, when it wants the Fibonacci of 1, it goes to the cache. When it wants the Fibonacci of 2, cache. Okay? And that's why it's so fast. Each Fibonacci sequence is only calculated once, and the cache is reused. Also notice that because of the way it's structured, you can see the linear time dependence here. So, now why is this working? So the definition of Fibonacci is calling itself recursively. This is very important. This is a sentence that confused me no end. That's what recursion is, right? A recursion is a function that calls itself. What happens when I memoize a function that is supposed to be calling itself? And the question is, which it do I mean after I've memoized it? Right? These are the ones I was worried about. I already knew it was working. I was thinking, I memoized this function, but it's calling fib inside. Which one does it get? Why is this working at all? Like, I was just confusing myself, is essentially what happens. And you always do this when you're trying to explain something to a trainee. Always. Like, I'm explaining this to you, and you are nodding your head, but I am super confused right now. That's what happens. So, what exactly is going on? So clearly, it is finding the decorated version instead of the original one. That's, well, right here, where did it go? Clearly, it's hitting the cache perfectly. It's working. It's a perfect example of decorators. But why? And then again, is it calling itself? Or is it simply calling a function named fib? Right? This is essentially I'm giving you the answer already for why it's working. But we'll dig a little deeper. So let's take it apart. So here I have the same idea, same memoization decorator, no changes. I call fib, but instead of decorating this, I create an alias, which is the memoized version of fib. Okay? So fib is still the same, and alias is the one that has been, you would call it decorated, but technically it's been wrapped and ejected out. Now, if I call alias of 3, the cache isn't getting triggered. When I call it again, the cache does get triggered. But if I call alias of 4, no cache in sight. Right? So it's not just so this is clearly different than slapping the decorator on the function itself. Right? At this point, I'm even more confused. Like, what? So it gets worse. But in getting worse, we'll get to the insight. What if same decorator, no changes. Here, I have the same original function. I pass it in. After I have passed it into the decorator, I set the variable fib to none. Okay? So I defined a function. I passed it through a decorator and stored it in another variable. And then I renamed the original variable for that function to none. And at this point, you're saying, this guy is crazy. Good. So now if I try to calculate alias of 4, you'll notice that this line is getting executed because I'm seeing fib of 4 here. But I get an error on this line here, which says, none type object is not callable. So it's able to access this function object only at this point where it makes an explicit call to a function that should be called fib, does it hit none and error out. Like, okay. It gets much worse. No decorator. Okay? Perfect example, right? We're talking about decorators, there's no decorator anymore. Same function, I just alias it. This is just another name for this function object now. And then fib, I set it equal to none. I call alias of 4. Same error, same line. It's able to enter the function object but only here does it error out. What's going on? Okay? So some of you are probably already there. For those of you who like disassembled functions, so if you don't understand this, it's not important. I mean, 99.9% of Python use gets away without having to look at a disassembler. But for people like me who like to confuse themselves, fantastic tool. So this I'm talking about the decorated function. So you'll notice that num, cache, and here is the critical one where it's calling the original function getting passed in. So that's just the decorator working, nothing special here. And then I was like, I need to access the actual original function. To that end, Python has this the dunder closure attribute. And this is what I love about Python is, Python has made like I'm saying even a habit. Python likes to like dirty its dirty laundry like out in the open. Like, this is how we do this. You want to find out where the thing is inside the closure? There's a dunder closure attribute. So I call the decorated version. It gives me a result. I call its dunder closure method, and it contains two cells. You'll notice that one of them is a dictionary. The other one is a function object, which makes sense. The closure is closing over the cache dictionary, and it needs to have access to the inner function. So good. And I can access it in this weird way, and I'll notice that I called fib of 8, and here is the cache dictionary, right? 8, 7, 6, 5, 4, blah, blah, blah. So this gives you insight into how it's working. What I want is I want to disassemble the inner function, the original fib, which I passed into the decorator. So blah, 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 here. It loads a global object named fib. That's it. That's all there is to this whole confusing mess. The fact that Python is actually being extremely dumb when you get memoized recursive functions. Here I was thinking recursion was being implemented in this some abstract, super complicated way, and the decorator was doing something magical, while in fact, one could technically claim that Python doesn't have recursion at all. That when you call a function inside, by its name inside itself, it doesn't even see that as a recursive call. It just says, find an object with this name and use it. It doesn't care that it happens to be the same function itself. This is exactly why the decorated version works. So if I go back, yep. No, here, where's the good one? Sorry, I hate it when people do that, but here. So even after memoization, when I call, let's say, fib of 5, it will go in here, it will say it's not in the cache, it will say call inner function 5, 5 will come up here. When it says find the fib of 4, it will say, okay, like any other function call, or really any other object use in Python, it will say, find me the object with name fib, load it, and pass in this argument. So once I have decorated the function, when I say fib, what does fib point to now, after decoration? That's what decoration does, right? The decoration takes the function object, decorates it, that is, wraps it, creates a new function object, and then reassigns that new object to the original name. By doing that, you automatically get this to call the decorated version of the function itself. So it all works perfectly fine by being as dumb as possible. It's a simple consequence of how the language is implemented. And that to me is absolutely fascinating. That a very basic design choice in the construction of the language, the idea that we will do nothing smart about any of this, and every time you find a name, just look for it through the LEGB scoping rules, and whatever you get is what you get. And you get this very fascinating complexity out of it for free. And the downside is that there's no optimization to any of this. Like if you're from Haskell, you can do all sorts of fascinating talks about tail recursion and stuff like that. But Python, Doesn't care. That's why I tell my trainees, day 1, hour 1, minute 1. If you want speed, Python is not for you. But that's a good thing, right? That's one of the pros of Python is they don't focus on speed, they focus on simplicity. And from simplicity comes complexity. Okay? So that's pretty much it. We can discuss other stuff. So here's the conclusion. The conclusion is when a recursive call is made, Python is actually only looking for a variable with a specified name, nothing special. If the name is rebound after the function definition, the recursion breaks. So Python doesn't keep track of any of this. Because it's an interpreter language, it only goes looking for fib when the interpreter gets to the recursive call site. And then it says, give me. It's just like, oh, I need to find fib. Where's fib? Where's fib? Whatever it finds, it uses. So you can break this. Since the Py syntax explicitly binds the function name back to its decorated version, we get a recursive call automatically. And that's the answer to all my confusion. So again, I'm at Bloomberg. We are always hiring. If you are like a new CS graduate, you might see me if you are hired, which is very likely. And then, thank you very much for listening. Questions? Anyone? There's one here.
I've played around a little bit with this memoization on the Fibonacci actually, and when I tried, I think Fib 1000, you get a max recursion reach.
Yes.
Can you explain what's going on?
So even with the memoization, if you see the, I'll show you the call graph with memoization. Right, so you see this is still a recursive call. So if you do like Fib 1000, it's going to be calling 1009 blah blah. So it's still slapping 1000 items on the stack. So you're going to get a stack overflow. But it's not going to be as bad as it was without memoization. Yes?
Do you use recursion in production?
Do you use recursion in production? Absolutely, as much as I can. In fact, the functional programming language paradigm, so Python has like 3, it essentially has all 3 paradigms, right? In Python, you can do imperative, you can do object-oriented, and you can do functional. And the functional paradigm essentially lives for recursion. But the downside, as I said, is it's not optimized for recursion. A language like Haskell, which is pure functional, is optimized for recursion. It can do some fascinating things with recursion. But recursion done naively can come at a cost. You had a question, sir?
Yeah, I think I might have figured it out while you were discussing. There was one example where you set alias to the fib, no decorator.
Yep.
And then set fib to none.
Yep.
The first call to alias actually called the first version of fib.
Yes.
Why did it not just return? Why was it not just none?
So initially, when you define, so what happens in Python when you define a function? You say def, fib, and you have a body. It creates a function object that has the functionality, and then it creates a pointer from the name fib to that object on, I guess it's the heap. When I say alias is equal to fib, I create a pointer from the name alias to the same object, and I increment the ref count to 2. Then when I say fib is equal to none, it breaks the first connection, but the second one is still valid. But when I now call alias of, let's say, 4, it gets to the function object, it starts executing, but when it gets to the recursive call and it says I need to calculate fib of 3 and goes looking for fib, that's the key here. It finds none, and then it breaks down.
I thought that fib would point to none, and so that when you set alias to fib, it would go straight to none.
Yeah, no.
But I see.
Yeah, that's the whole model of Python, right? Anyone else? Okay, if not, we will have a little extra time before the next talk.
Thank you.
Thank you very much.